Hey guys, can you hear me? Didn't somebody? Okay, great. Thank you for confirming. Oh, okay.
See?
Good to check.
Yes.
Okay, can you hear?
Yes, now we can hear.
Okay,
Thank you.
good. Sorry,
Thank you.
we were muted. So welcome everybody. It's a pleasure to have Naz here with us today. Naz is a fourth-year PhD student, so close to graduation. Hopefully, yes. At UC Santa Barbara, and he's working with Jonathan Balkin, that most of you know. He was visiting us last year and 2 years ago, and he's collaborating with many of the students here at BSc. And Naz is doing a PhD on hardware software co-design with a strong focus on accelerators and all the software layers to connect with the accelerators. And today you will be talking about Pengwing, which is the more recent paper that you are working on in your thesis.
Yeah.
And let's see how it goes. So thanks a lot for coming, and the floor is yours.
Yeah,
Thanks.
thanks for having me too. So before starting, I can talk shortly about myself, but it's already introduced. I work on computer architecture and I did some internships in the past. So here now I'm happy to learn about HPC stuff at BSc. And originally I'm from Kazakhstan. We love to say that we are in the heart of Eurasia. So just small introduction to my country. And UCSB is located like in California. It's like part of this like a UC network of universities, University of California. So in terms of contents, yes, today I'm going to talk about blended OS or Pengwing. Pengwing is like an implementation or prototype of our idea, which is called blended OS. So that's why we have two names in case if you might get confused. And then before talking about that, I will lead into like what is heterogeneous SoC in general, what is a problem statement, and then I will introduce our solutions. Then like in terms of the background, so what is heterogeneous SoC? So heterogeneity refers to the difference of components in our system on chips. Usually originally we started with big little CPU cores, which refers to the performance or power cores in our SoCs, but now we are featuring more and more accelerators, which are special purpose computing units that can do only one task, like let's say machine learning or encryption. Why? Because we want to reach optimal performance and preserve power at the minimum area in comparison to CPUs that can do everything. And so as a result, we're ending up with a sea of accelerators. And here, for example, we can see that a lot of applications, user applications have been accelerated. Most of them are graphic applications, some encryption, machine learning, and a lot of floating point heavy operations as well. So why we have accelerators, again, to explain a little bit more, is that other than optimizing for certain operation, having only custom version of it, you can also optimize for not only computation parallelism but memory level parallelism. You can have a better cache performance. You will not trash your cache if you'll be running only, let's say, all application only in a high performance CPU core, because one accelerator will be using one application will be using one accelerator. And then these accelerators are common usually in mobile SoCs, but used in many other hardware as well. And so other than that, we also see in more interesting types of applications, actually system services being accelerated, which are, for example, memory allocation or page fault serving, or even garbage collection. So as we can see, this is also driven by the fact that software stacks complexity is increasing over the years. And then so there is now increased interest in accelerating system services in the hardware as well. As a result, we are having even more increased hardware heterogeneity. So then question is, then can we afford all this heterogeneity? Can we actually build a system that we can program and which is efficient in terms of communication overheads with all these accelerators together? For example, what is a how this complexity will affect the programmer productivity and orchestration efficiency, which means a communication overheads in between all these accelerators. So then as a short answer, at the moment, answer is kind of close to no, because we don't have no uniform API that will connect between different type of accelerators. In fact, accelerators have different types like streaming or request response based and specific to different vendors who develop these accelerators in comparison to, let's say, just a uniform Intel or ARM ISAs, right? So then all the CPUs accelerators don't have any idea of each other's existence, and developer, when writing a program, needs to navigate all this knowledge from different APIs and complex driver logics and different assumptions that will make these accelerators work the best. And in addition to it, there is no OS support for building system with different accelerators as well. That is, there is no let's say, built-in some services or some features that will help to these accelerators from the OS part that will make developers' lives easier. As a result, we cannot build this kind of exciting system where everything is connected to everything else. And this is a problem statement that I'm trying to solve during my PhD, and I will present these two works that we are building. So cohort, this is a work that we have already published in us+, and this is what we term as software-oriented acceleration. The idea is that to extend the common well-known software semantics to the heterogeneous SoCs as well. Why? Because we already know that these things work. Programmers know about all this like a high-performance solution for the CPUs, but then we need to figure out, so there will be not too much overhead for like learning curve for developers to learn, but then we need to figure out how to connect it to the accelerators so that accelerator designers now will not be constrained by these existing methods. Accelerator designers should be still able to develop like very highly performant custom hardware designs. So the idea is that then we can like use shared memory queues or like a software producer and consumer queues that are well known in the software world to accelerators to do communication between the CPUs and accelerators. Also, accelerators with each other should be able to communicate by these producer-consumers queues directly as well. And in terms of then implementation, so at the software API, we have just like shared memory queues. So whenever developer wants to put the data into the accelerator or another CPU, it can just use push API. And when getting the data output from the accelerator back, it can just pop from the queue. And in terms of hardware, to make it actually possible for accelerators to understand that these queues exist, they can, like we have the wrapper with accelerators that has its own memory management unit, which can translate from virtual memory to physical memory, because usually accelerators work only with the raw data. And then there will be also queue trackers that will track the input queues if there is like any new entry, if the queue's tail pointer has been increased. And this is implemented by like a shared memory. So we like a cohort can attach to any coherency system in the SoC and can listen for the messages of like tail pointer being updated or not. And feature-wise, like why do we have it, right? Other than just like easing this communication between accelerators and CPUs, we can use all these like well-known software features like batching optimization. So instead of like incrementing your tail pointer by 1 or 2, you can increment it by like 256. So in a way, cohort is going to fetch all these 256 entries of the queue for you like directly. So you don't have to go back and forth. And then you can also optimize for the huge pages, which means that when translating from the virtual memory, you don't have to translate at the granularity of 4 kilobytes, but you can translate at the granularity of like 1 gigabytes or 2 megabytes, depending on what is your setup, and many more. So that's the benefit of having like this like software-oriented mechanisms. And then now in terms of implementation, here we have a code for like a producer consumer code for single accelerator. So we definitely need to first create these queues in the software. So it's just like initialization functions that consist of like allocating the memory for the queue of size X and like assigning the metadata. And cohort register function, through the use of this like uncached registers here, it will write the data into this like registers of the accelerator of cohort. And then the rest is just using push and pop functions to get the data out of the accelerator. What specifically happens here is that whenever, so our queue has tail pointer and head pointer. Tail pointer refers to the like where the like last data has been added into the queue. And so whenever it's upgraded, invalidation message will be received by the cohort because cohort participates in the coherency system in the SoC. And after getting the invalidation message, it will go load the data from the queue at the index of tail pointer. And when receiving that data through the consumer endpoint, it will feed it into accelerator. Accelerator does some operation with it and puts the new data into the output queue, which in its turn now going to increment the tail pointer of the output queue. So in our situation, it's like result 5.4, right? And then this data will be received by the CPU in the end. And so we had this like a code snippet with a single accelerator, but now we can chain accelerators together, which is a cool benefit. For example, output Q, output Q of the like first accelerator, for example, AS, can be input Q of the second accelerator, let's say SHA. And then like a CPU doesn't have to participate in this communication between these two accelerators apart from like at the very beginning registering these functions. So this is this like implementation of like how these like three different queues can be created and chained to each other. So in this function, we see like inputs and outputs assigned accordingly. And also these like functions can be deregistered and registered to different accelerators at the runtime. It doesn't have to be static for the entire duration of the program. So this is like how we can build like applications with cohort. And in terms of the, and this is kind of what we implemented in our prototype, not kind of, we implemented it. So Ariane is like refers to the like RISC-V cores, 64 bits as it puts Linux, and we have this like AES and SHA accelerators. Then these are like our speed up numbers. So we can see that like a different accelerators will feature different speed ups with the cohort, because of the like latency of each accelerator, how much it will benefit from prefetching the data or not. So how much useful work it can do like while waiting for the data and stuff. So we see that like and our baseline was a comparison of cohort into other classical data movement methods like TMA and memory mapped IO. So because and as a result, we said like we saw a maximum of like 11 times performance win when we like move data at a like more smaller granularity, and at a higher data granularity, or like when moving larger data, we have slightly less. So it's all about like managing between the like how much overhead of like traditional methods, and also about how much cache size we have in our SoC that can benefit from this like a software-oriented mechanisms. And we also showed in our paper how much like a cores can be efficient, or like an instruction per cycle performance speed up we observed with cohort. We see like up to 4 times like a IPC speed up over MMIO and DMA methods. Over MMIO and over DMA, we have up to 2 times, and similar-ish performance wins with a yes accelerator. So SHA has like a more latency, so we have kind of more speed up with SHA. So now our main work, Pengwing. So in earlier paper that we presented this like a communication between accelerators based on single producer, single consumer queues, but then we need more in making heterogeneous SoCs possible. So we need like actual operating system support, and this is what this work is for. And we have some collaborators from the BSc. And generally, this consists of a lot of people who worked on this project. So what we have here, the idea is that we have like a regular conventional OS, and we have our blended OS idea. With a conventional blended OS, to mention again, accelerators are treated only offload only unit. So like operating system is not built around it. And so if like accelerator needs certain service, it cannot request it on its own dynamically. In fact, developer is the one who is going to write all this like a heavy code to say what will happen if like a software like has like a page fault, or like a software actually needs to allocate all the memory for the accelerators and calculate everything statically so that like abnormal behavior will not happen. So it requires a lot of like a coding from the developer side, and there is also additionally, there is like actually no idea of even runtime to observe what's happening with accelerators, like or not, between accelerators and the programs running on the CPU. And as a result, there can be like the code will not be flexible enough, and there will be a lot of like communication overhead because you need to like go through all these layers. Like from the application to the hardware, you need to go through either runtime or kernel. Even if you bypass, there will be like a complexity of writing that like actual kernel bypass code. And if from the hardware, there is no way you can go up, connect directly to the application stack, or like let's say request some like memory allocation service. So what we propose instead is a blended operating system where we say that no matter what is your privilege level, you can use like shared memory queues to communicate between all these accelerators and applications running on CPUs and services. And how do we do it is it is based on the three principles that we show here. So which are liberty, equality, and collaboration. If you think it reminds you of some French Revolution ideas, you are right. We are partially inspired by it. They match in a way. So liberty here is about developers should not be constrained in terms of both communication overhead and the programmability when choosing between the CPUs or accelerators when placing their application program or system service. So as a result, it can use any of the version of the application logic. And equality refers to the idea that accelerators themselves, if they want to communicate to another accelerator or another software or another system service, they should be able to do so without calling some software glue or some other third-party logic. So, and operating system should be able to have support for both of these principles. And now when it comes to the collaboration, this is about not only sharing the data in the queues by feeding this data or the pointers, but it's actually sharing the data structures beyond the queues. So let's say they are sharing the heap. So if there's some objects that exist in the heap that are not passed through the queues, these accelerators should be able to still parse those heap objects by the pointers that are passed from the queues or beyond. If some data structures have been sent through the some configuration. So this is the idea of sharing. So accelerators don't have to always share their data structure with other accelerators or other CPUs. Sometimes they can operate just siloed. For example, encryption. Encryption gets a raw data, and does encryption gives you data back. It doesn't need any metadata to do this operation. But if you're doing garbage collection, then you need to know where the root address is allocated and how things how objects are linked to each other. What is this objects of the language runtimes that uses it. So you with the blended OS, our idea is that you should have all this flexibility. If you want to share your accelerator with other accelerators or CPU, you should be able to do so. If you don't want to share, you should be able to do so as well. And this is based on this existing operating systems, but for multi-core systems. For example, if you already know about Linux, where you share everything. Everything is based on the shared memory. If you want to message passing, you can do it as well, but it has a lot of flexibility. But then we have other operating systems, if you maybe know, called Barrelfish, FOSS, or K2. So Barrelfish is a multi-kernel operating system, which assumes that number of the both FOSS and Barrelfish assumes that the number of the cores in the modern SoCs will be massive, thousands of cores. So then a shared memory will not be scalable enough. So they use just only message passing, and every kernel will be running on this every CPU on its own. FOSS takes it a bit on the other extremes, that not even kernel, but system services memory allocation, let's say, can be run in different how to call it, CPUs, and they can all use message passing. So it's even a finer granularity. And then K2 is about having heterogeneous coherency domains. And so if developer will choose, let's say, more independent or more private or more shared, then it can implement its system services in all these different semantics. So it lets you use to both shared memory or message passing. But the idea is that we have so many great operating systems for multi-core homogeneous SoCs, but not for heterogeneous accelerators. So this is the features that we want to provide. So this is a SoC prototype that we built and emulated on FPGA. We were able to put Linux on this. So we have 9 tiles where we have 3 RISC-V cores, and we have 6 accelerators. Key value store, garbage collection, memory allocation, encryption, decryption, and networking stack. And so if you're wondering, well, what are the examples of like that can get the benefit of blended OS, is we have now like different use cases. So the first use case will be running and utilizing on Aryan, Malloc, and garbage collector. So 1 CPU, 2 accelerators. What happens here is that it's about cooperation between software thread, garbage collection, and memory allocation. So let's at the beginning, let's say software running on Aryan is going to request some memory for a certain size. It will get the data, do some operation to it, and at some point heap is low in memory, so it needs to invoke garbage collection. And then garbage collection will start marking the objects and sweeping them. But instead of overwriting and clearing all the objects on its own, it can send the pointer to the cleared object to the memory allocator back, so like as a free call, so that memory allocator like can use it when next time CPU is going to request some like addresses and buffers. And the second use case can be as simple as like a Aryan and key value store accelerator sharing the heap together as well. So anytime when Aryan will send the key request, instead of doing it in a software, which can be expensive because key value store applications like Redis or Memcached are very irregular, so like the accelerator can be used. And third use case that we can have is with Aryan core, with a memory allocator again, and networking stack. So what happens in this situation is that usually like developers will statically allocate again all the packets for the networking stack. But what happens is that often networking stack comes with the packets of different sizes. It's not always like a 1500s of bytes, which is I think is standard, but then or default minimum size. But then like it can be much larger than that, like 2K or 6K, or maybe smaller as like a 512 bytes. So in those situations, networking stack, when it receives the packet, it can allocate the buffer like on its own by requesting from the memory allocator without the CPU. And it will write all the contents of the newly arrived packet into this buffer and sends a pointer to it to the Aryan core, so Aryan can does whatever it needs to do as a software. And then Aryan can send this like a buffer back to the memory allocator so that it can freeze that object, or it can use it for new allocations that can be coming. So this kind of gives like a lot of flexibility. It can make us use memory more efficiently, and obviously like less memory overhead, because CPU is not much part of this like communication between accelerators. And how we enable it. So if you remember about cohort, it was about having SPSC queues between accelerators. Then with Pengwing substrate, we are building a substrate that now consists of multiple features, not only SPSC queues. So accelerators now, which are like can be Malloc or GC or KVS or anything, now having access to multiple SPSC queues instead of single SPSC queue, and it has access to multiple producer, multiple consumer queues, and it has access to load store unit, so that whenever the contents of the queue doesn't have to be only raw data, but it can be a pointer that can be fetched as well. So the idea is that by providing all these like interfaces to the accelerators, we can build very flexible and powerful systems. And like it doesn't have to like every accelerator doesn't have to choose the same amount of queues or LSU interfaces. They can choose different amount. So here in this example, we have, for example, memory allocator having like 2 SPSC queues, but 1 MPSC queue for, let's say, 3 operations. And a key value store accelerator uses only 2 SPSC queues. Garbage collector and networking stack uses higher amount of queues. And so now here we have like experimental results if you're concerned about, well, what is actual performance benefit? So we have numbers here for use case 1 and use case 3. So here use case 1, if you remember, was about garbage collection and memory allocation and software stack, sharing their states together. And so here, GC marks and sweeps objects that are created by allocator. And as we can see, we tested with different heap sizes, and we have like tested a small heap sizes like 200 kilobytes around, and the largest we tested was like a couple of megabytes of the like a heap size. So we see that there is like a consistent growth in GC accelerator performance. And it shows how like certain services are very suitable for acceleration, and how like by the cooperation between the accelerators we can benefit a lot. Well, the reason why is that GC has like features a lot of memory level parallelism. For example, for marking, it's like a lot of memory operations that like it traces like a heap objects, which can be like a sort of a graph object. And then when it comes to sweeping, it's just embarrassingly parallel process where you just like send these like requests to the allocation accelerator saying, and they are all independent from each other, right? Because it has been traced already. So it's just like how many ports you have, you can just send all the operation to the allocator accelerator. That's why we have like a hugely increasing performance. And the limiting factor here is going to be definitely like cache size, like the capabilities of the SoC. The similar limiting factors as like, let's say, multi-core system will have. And definitely one can build like even better garbage collector accelerators. Our version was like stop the world GC, but if you want to do a more concurrent accelerator, you need to deal with some locks, but it should be built as well. It can be built as well. Now for our second use case, what we have is Metal. So it's a name of the key value store accelerators that have been implemented in the past, but it have been implemented in Gem 5. So we re-implemented it like in our own OpenPython SoC. So we tested it with a Redis application actual, and what we tested it with like thousands of like requests up to like 1 million requests. And what we saw like a consistent, like a 2 times like performance improvement in like serving this like a key value store operation in a software versus in a accelerator. Like even like, thinking of like all this cohort communication, everything included. So we still have so much performance benefit. Which shows how much like integrating accelerators into your system and providing this flexible operating system support and communication support brings you. And so then now in terms of like future work and traction, we have like implemented our like SoC Pengwing with blended OS ideas for like more like a classical accelerators, like more like a classical mobile SoC applications. But what happens when we, let's say, port with AI or HPC is kind of another question, because the more data is flowing, the bandwidth will be more important. And for example, maybe HPC application just like do everything statically. Now the question is, does it has enough dynamics in it? What are the like painful moments maybe you guys had when like building this AI and HPC with like a classical CPUs and GPUs? I would be excited to learn more about that. And your thoughts on accelerators. What kind of accelerators have you guys already employed, used? What you loved about it, what you hated about it? So I would love to hear about it more, and that's the reason why I'm here. And then in terms of like next project at the BSc itself, now we are looking more into event detection and notification distribution for systems with accelerators, because here, for example, we see how like accelerators exist, and we like solved all this problem with like data communication and runtime, right? We attempted to solve. But then what happens if some abnormality happens, like some process will die? How how accelerator will know that that process died. Let's say that like we are implementing concurrent garbage collection, so you are sharing your heap and objects, and you need to like wait for the mutator if it's operating on the data already. So then locks are in place, and how we gonna like know about them? Should that like a lock mechanism be part of the substrate, or can there be another micro engine that's tracking all the locks for you and distributes all the events to you? So this is kind of some like other interesting questions that I will be looking forward to learn. Yeah, and this will be really good for systems with accelerators, but I think if we can solve it first by building some micro engine for system with without accelerator, with just CPUs as well, that can be a good starting point that we can, you know, extend to systems with accelerators. So with that, I think I'm ready to finish. And if you have any questions, please feel free to let me know, and thank you for your attention.
Any questions? Sure.
First of all, thank you for the presentation. It's very interesting.
Mm-hmm.
My just one question is about like security concerns.
Mm-hmm.
So what imply like this shift paradigm to the OS? I know like classical one is more like constraint, but at least guarantees some security features, let's say.
Mm-hmm.
What the concerns here if we are going to shift more distributed service oriented feature?
Yeah.
So let's repeat the question so that the people on Zoom can understand what you're answering, please.
Okay, good point. So the question here is about what is like security implications when like a shift in the paradigm from more constrained operating system to more like a graph-like operating system, or new ones that we're proposing here. So the idea is that we are reusing whatever exists in the like classical operating system in terms of memory and virtual memory, pages, and other abstractions, right? So whatever you security protections that you have in terms of like rights for read or write or execution, all these bits, like when you read and translate from the virtual memory address, will be still there. So essentially, like all the basic securities in terms of virtual memory abstractions will be there. So we are not compromising anything by building blended OS here. You might have then concerns about what about the drivers. So then you can think about more about that. But again, like even in a classical operating system, you have like drivers. You need to make sure that they're compartmentalized and stuff. So the same constraints will apply here. We're just giving more flexibility. Like if you are more concerned, you can kind of make sure that like a accelerator will go through like access the driver logic first before accessing the accelerator, but your driver logic can be like have like be another accelerator, which is like you can make sure that it's secure, right, by design, because you are building it on your own. Because in your SOC you're gonna have like more like a trusted, let's say, accelerators, and not trusted, maybe it's the same way as you can have like more trusted code and not trusted code. When you write your application, you're gonna have different libraries which is third party, and you have your own library, right? So like you can use the same mechanisms, but if you're absolutely concerned about the safety and security, there are like systems like cherry capability and stuff, so you can like build with that. We haven't done that because it will like be a lot of engineering work for us, but people interested can do that.
Okay, so the answer is that there are no extra security concerns because of the blended OS.
Yeah, because we are basing off like on the classical operating system features. We're just like let's say transforming vertical stack in the horizontal, but all these like features are still there. Like you can reuse like all the assumptions.
Yeah. Okay. So you are convinced?
Yeah.
Okay, good. More questions.
I want to ask about the virtual memory.
Mhm.
Like then you have cohort,
Mhm.
right?
Yeah.
That manage all the virtual memory and coherence stuff. So then the accelerator, I guess, doesn't care about, doesn't use virtual memory, just physical memory, I guess.
Mhm.
Then it's a possibility that you have a accelerator that wants to use a virtual memory.
Yeah.
Like how will work with cohort and big bang.
Wait, can you repeat your question? So the idea is that are we having assumptions that accelerators can already work with virtual memory, or?
Yes, sorry. So I guess that now your assumptions are that accelerator doesn't work with
Yeah.
virtual memory.
Yeah.
What happens if it works with
Ah.
virtual memory?
Well, then it's
That
already.
So what happens to her approach, or what is the hardware support or software support that you need to enable that? I'm not understanding the question, sorry.
Yeah. So yeah, what do would need to enable that?
Okay.
Yeah, well, if like accelerator already works with like virtual memory, then I think it's good for us because okay, yeah, I see what can be happen. If accelerator already works with virtual memory, it means that it has its own MMU and maybe it has like its own like a translation assumptions and mechanisms. So then like a question can be about whether we can replace our own MMU or their MMU, because we are using right now not like a custom MMU, we are using like RISC-V CPU's MMU. So like we are not doing anything specific to cohort. We are reusing like classical CPU, how to call it, MMU. So if they are similar, that we can replace their MMU. If they are not similar, then we can try to adapt to that MMU. So there will be some hardware work done, right? But then it will be just like a one-time hardware shimmer that you need to write. Yeah.
And this is because of the blended OS, or all hardwares that need virtual memory would also need this support?
So like it depends like how every accelerator comes, right? Because every accelerator usually comes with their like own package and stuff, and we try to like reduce it at the like design time by like having our own substrate, right? So if accelerator can be attached relative to the substrate, then it's good. And I think having their own virtual memory as being able to work with the virtual memory, I don't think it should be constrained for us. Like I would imagine that most of the situation, it will be readily attachable to our blended OS. But if there is some differences, we should be able to attach anyways as well, because underlying assumption is that like you can have like a SoCs which are run with multiple coherence domains. So so it's not like a news, right? Like having like different maybe virtual memory assumptions or coherence assumptions. So we can use the best expertise from like what we did in the past when we port new accelerators as well.
Good. Any other question?
And Nara has some.
Nara?
Yeah, so you said that you have been testing this on OpenPython, right?
Yeah.
So my question is, do accelerators connect with the standard 3NOx, or is there like an additional network for communication?
Yeah, like a standard, like what is in the PMesh, like we have it directly. So let me go back to the cohorts. Yeah. So as you can see, cohort, like accelerator doesn't connect to anything by default, right? But then we have cohort that talks to both L15 and PMesh routers. So we can access like L2s in other places, or we can access our own private L15. And if there will be like a local cache that comes like with an accelerator, then yeah, there needs like cohort can be connecting to that as well. And there needs to be some, I believe, translation, but other than that, things should work.
Okay. Any other question? Maybe someone from Zoom wants to ask something? No? Then otherwise I think we can close the seminar here. So thanks again to Nas for a nice presentation, and come back soon.
Yeah.
Oh, sorry, no. Come back soon. Sorry, my bad. Nas
I'm
will be
still here.
You are not leaving. You are still here until
July 31st.
so 2 months and a half. So if you are interested in talking to Nas, shoot her an email. She's normally in the TLS building. And if you don't find her, I mean, tell us and you can meet with her. So she's very interested in HPC applications and potentially using these applications with some accelerators.
Yeah.
So this is basically the goal of the internship. So that would be good. Okay, thanks a lot.
Thank you.
Mhm.
Thank you. Bye.
I stop sharing.